This is a 50 session on the topic design of stage projects. So in this week you might have studied about different tension levels. So as we have studied in the last week, introduction to tension member, what are the tension member, what are the different type of tension members. In this we will study about how to do the design of tension members. Basically calculation of net area, then strength calculation, and then adding the connections to it, and what are the different design steps of the complete tension member. So if we go from the basics again, if we go from the start, what are the tension members? They are the structure members which are subjected to axial tensile forces. Mainly, if we see the truss members of our bridges, the cables in suspension bridges or bracing for our buildings, they are the few examples where we can say they are used as a tension members. So for the tension members, normally we can use any type of cross-sectional area. It can be I section, C section, or any type of build-up section. And since why we can use any type of cross-sectional configuration, because the only detrimental of strength is the cross-sectional area. So any type of configuration is okay with these type of tension members. And if a member is carrying direct tension, then that member is called as tie. So this all we have already studied in last week. If we now, next thing is, if we go to the design strength of tension member. So the first step is first we will calculate the factor design tension. So the factor design tension, whichever what we are calculating, should be the tension should be less than design strength. So TD is our design strength, so the tension force we are calculating, it should always be less than the design strength. And TD is the lowest of the design strength due to yielding of cross-sectional area and rupture of critical section and block shear area. So out of these three type of tension force, whatever would be the minimum, we will take that as the design strength of our member. Okay, second thing is under axial tensile force, we are calculating under axial tensile force, we are calculating TDG. So TDG is the yielding of the cross-sectional area. So how we are calculating? It is given by area into stress divided by gamma m naught, factor of safety. So AG is the gross area of our cross-sectional area. If we say B into D normally, so that will be our gross area, and then Fi will be the yield stress which will be given to us, and gamma m naught will be the factor of safety, and it will depend on the radius factor as given in the table 5 of IS 800. So next thing is, if we are designing plates, so this design was for the normal tension members. Now the second step is, if we are designing plates as a tension member, then our TDN is given by 0.9 AMFU divided by gamma M1. So Fu will be the ultimate stress. It won't be yield stress in this case. The previous case we have seen, we are using yield stress. In this case we are using ultimate stress, and AN will be the net effective area of cross section. Instead of gross area, we are taking net effective cross sectional area, and gamma m1 will be the partial safety factor at ultimate stress. There we are taking partial safety factor at yielding. Here we will be taking partial safety factor, this is gamma m1 at ultimate stress. So if we are designing threaded rods, this TDN will be similar as we have seen before. Only change will be the area, effective area will change, it will be the net root area of the threaded section instead of effective area of the complete cross section. Okay. So other things which can be designed as tension member are the single angles. If we are using single angle section, and then the rupture strength of the angle connecting through one leg is affected by shear lag. The design strength TDN is governed by rupture at net section area. So this will be a design strength, and it will be given by 0.9 ANFU divided by gamma m1 plus beta AGA FI gamma m1. So this is this part which doesn't have any connection plus the part which have connection. So the part which have connection, there we are taking one factor beta, and area is changing as AGA. So beta will be equal to 1.4 minus 0.076 W2 FU upon Fi into Vs upon Lc. So these all formulas are already given in IS 800. You can directly use the formulas from there, and this value should always be less than Fu gamma m1 divided by Fu gamma m1, and should always be greater than 0.7. So W is the outstanding outstanding leg width, and here, and Bs is the shear leg width. This is our shear leg. This will be our Bs. W plus W1 minus D. So W plus WF minus this thickness D. So that will give us the shear leg width. That means this part plus this part. This is a shear leg. So W plus WT minus 1 time thickness we are doing, because this part is overlapping. So that will be our BS, and in this case if we have the welding joint, then our BS will be given by only W. Okay. And next thing is the LC is the length of the end connection. So in this case, this LC is the length of the end connection, that is the distance between outermost bolts in the end joint measured along the load direction, or length of the weld along the load direction. So for preliminary sizing, the rupture strength of net section may be approximately taken as TD is equal to alpha AN FU divided by gamma M1. Okay. So here alpha is given by 0.6 for 1 or 2 volts, and it is given as 0.7 for 3 volts and 0.8 for 4 or more volts. So if you go to the next thing, first we have seen the design strength normally. If we have a block shear case, then our design strength will be changing according to our type of connection. So if we have a bolted connection, then our block shear strength TDP of the connection is given by ADG Fy divided by under root 3 gamma m0 plus 0.9 ATN Fu divided by gamma m0. So this is the case when we have shear yielding and tension failure. So if it is the opposite, if we have yielding in tension and fracture in shears, then our formula will change accordingly. This part will come here, 0.9 AVN FU divided by under root 3 gamma m plus ATG FY upon gamma m. Okay. So what are the different area we have? AVG and AM will be the minimum gross and net area in shear along whole time parallel to external force. So as we can see here, uh, if our load is in this direction, so area among 1, 2 and 3, 4 will be given as AVG and AVN. Or in this case, if we see, it will be this part. And in the next thing is the ATG and ATN. This is in the net area in tension from the bolt hole to the toe of angle and bolt line perpendicular to the line of force respectively. So if we see, this is perpendicular to the direction of force, that area will be given as ATG and ATN. In this case, it will be full area. Okay. And last thing is FI. FI will be the ultimate and yield strength of the material. Okay. FU will be the ultimate strength. FI will be the yield stress. So next thing is, in case of that was the case if we have bolt joint. In case of a welding joint, the block shear length TDB shall be checked for the welded end connection by taking an appropriate section in the member around the end weld, which can shear off as a block. So that will be the case in the welded section connection. Next thing is, in case of tension member, what should be the slenderness ratio? So if we see slenderness, so next thing is, what will be the slenderness ratio in case of tension member? So slenderness ratio will be given by L upon R vector, right? So ratio of unsupported length and least radius of gyration. So depending on the what type of member we have, slenderness ratio will change. If for example, if we say tension member in which a reversal of direct stress occurs due to load other than wind or sea vapor, in that case we are taking our gamma as 180 CMD. Depending on the type of loading and type of member, our slenderness ratio will change. Okay. Hello. Hello. So this is what the we have design strength values in case of our tension member. Next thing is, what are the different design steps when we are seeing the tension member. So first thing what we are calculating is, we will calculate the gross area required to carry the given factor load TU, and the formula will be, area will be load into gamma divided by stress, right? So after calculating the area, we will select a suitable shape of the section depending on the type of structure and location of the member, such that the gross area is more than the gross area obtained in step 1. So we will select an area, I section, C section, whatever we are selecting, that so that this area is always greater than AG, which we have calculated in step 1. Okay. After calculating, after getting a suitable section, we will have all different properties of our section. From that, we will determine the number of bolts or the welding length required and will suitably arrange the holes. Okay. After calculating loads and everything, we will calculate different strengths. First is TDG, yielding of cross section, rupture at critical section, strength in block shear. We will calculate all these three strengths, and minimum of these three will give us design tensile strength. Right? So it is given if any of the above strength become less than the factor tensile strength TU, then you have to increase the section and repeat the from the step 3. Okay. Also, if the design strength minimum of TG, TDN and TDP is too high compared to the factor load, decrease the section size suitably and do step 3. So we have two strengths. We have factor tensile force TU, and then we have design tensile strength TD. So first thing is all three design strength should always be uh, greater than factor tensile force, and if they are less than, then we have to increase the section. Second thing is if our design strength is too high, it should be greater than TU, but it should not be too much greater than TU. If it is too much greater than TU, then we have to reduce the section size and again design the same thing. So after getting our section, what we are doing, we will apply some checks. So first check is the check for the slenderness ratio as per table 3, and if the value of slenderness ratio exceeds the value given in code, then increase the size of the section and redesign. Okay. So these were the different design steps for designing a new tension member. Second thing what you might have studied is how to use MATLAB algorithm to do the design of any tension member in your system. So this is the flow chart which you might be following for MATLAB coding, and this you might have already studied in the class, so I won't go for it. It is similar thing. First we will calculate the area required, then we will select the section, and if our section is if the length of connected like enough for bolt to fit, if it is yes, then we will go further. If it is no, then we have to repeat our step. Same way for the welding, this should be the condition, minimum length of welding required in the weld distribution. If it is yes, then we will go to the next section, otherwise again we will change the type of section we are using. So after getting everything, we are calculating the design strength of angle due to the next section rupture. Is in the safe net section rupture, if our angle is same, then we will go further. If no, then we again have to design our section accordingly. We have to change the dimension of our section. If it is yes, then we calculate the gauge length in case of bolts, then or in case of welding we will check for block shear failure. Then again it's completely same steps which we have done in like theoretically, just a flow chart of the same thing. Last step will be we will check for the slenderness ratio as we have seen before. If it is fine, then our section design is okay. If it is not fine, then again we will go back and design a section from the beginning. Okay. So this is all what you might have studied in this week 5. Next we will go to some question and answers which will help you solve the assignment for week 5. Okay. So the first question is, A factor beta is used while calculating the rupture strength of a tension member made of an angle section connected with either gusset plate or other section to address the issue of shear lag. The minimum value of beta is 0.1, 0.3, 0.5 or 0.7. Okay, so it is given in IS 800 clause 6.3.3. So beta value should always be greater than equal to 0.7. Okay, so minimum value will be 0.7. Okay. Okay, then we will go to the next question. A plate of size 60 mm into 8 mm is used as a tension member. Find the design tensile strength under gross yielding condition if Fe410 grade of steel is used. So, in this case, what was our first step? First step will be calculating the area. So, calculating area will be, if we are using normal plate, so area, gross area will be length into thickness, B into T, so it will be 480 mm. And for Fe 410, Fy will be 250 megapascal, and in this case, gamma m0 will be 1.1. Okay, this is the given condition. Now what we have to calculate? We have to calculate our design tensile strength under yielding condition. So design strength under yielding condition will be given by area into Fy upon gamma m0, right? Sena stress is equal to load upon area. So load will be stress into area and divided by a factor of safety. So Ag we have calculated 480, Fy is 250 and gamma m0 1.1. So our design strength will be 109.1 kN. Okay. Fine, then we'll go to the next question. The maximum slenderness ratio of member which is always in tension other than pre-tension member is given by this we have seen in that table to remember. So these are the maximum value of effective slenderness ratio. This is what we have asked. Members which are always under tension other than pre-tension member. Maximum slenderness ratio is given by 400. Okay. Fine. Okay. So we'll go to the next question then. Calculate maximum effective length in meter that can be provided for member BC. Let's say this is a member BC shown in figure below if its minimum radius of gyration is equal to 15 mm. Can I calculate it? So this is given as R minimum. We have to calculate effective length. So in this case, what would be our slenderness ratio? As member BC is a pure tension member, we see this member, it is always in tension. So according to table 3 of IS 800, maximum slenderness ratio for member will be 400. Okay. Now gamma is equal to L upon R. From here we can easily calculate our L value. So L is equal to gamma into R. So gamma 400 into 15 is equal to 6 meter. Okay. Okay, then we will go to the next question. Two plates of 180 mm into 10 mm size are connected by four numbers of 16 mm diagonal. If the staggered pitch is 40 mm, this is our pitch, this is our diagonal, and the gauge distance is 40 mm, this is our G value, and the edge distance is 30 mm. Find the net area along the line 1, 2, 3, 4, 5, 6 under axial tension. Okay. We will see the step-by-step calculation of this question. First thing is, we'll note down everything what is given to us. So diameter of hole 16 mm, diameter of hole will be 16 plus 2. We are taking the extra length for diameter of hole. It will be 2. 16 plus 2, 18 mm. Then P is given by 40 mm, G 40 mm, and number of hole 10 is equal to 4. Edge distance is given as 30 mm. So calculating the net area along this length, if you see this length, then it will be this is the formula already given to us in IS code. A is equal to B minus M dH plus sigma ds square plus 4g into complete thickness of our plate. So in this case, B is given to us as 180 mm. So total 180 minus n into dh. N is number of bolt. So number of bolt n into 4 into dh. Area dh is 18 mm. So this length minus 4 times of our bolt diameter plus which p square upon 4g into ds upon 4g sigma. So 3 times this is coming 1, 2, 3. So that's why we are multiplying it by 3 times and into thickness. So thickness of our plate is given as 10 mm. So adding up all the values, we are getting AN as 1380 meter square. This in meter only. It will be in mm square. So here it is written. It will be mm square. So the answer is A 1380 mm square. Okay. Then we'll go to the next question. Calculate the value of beta for a tension member made of ISA 75 into 50 into 80. 8. The larger leg is connected to a 10 mm gusset plate with 3 number of 20 mm diapole of grade 4.6 arranged in a single line as shown in figure. The pitch and edge distance and the gauge distance are, this is our pitch, this is our edge, and this is our gauge distance. This is all are given. Consider Fe14 grade of steel. So how we will calculate? We have a direct formula of beta. Remember? Just give me a minute. Okay. So what is given to us? Diameter of bolt 20 mm. So diameter of hole will be d plus 222 mm. Same as we have seen in previous example. Next thing is we have to calculate the calculate the value of beta. So for calculating the value of beta, first we need to calculate the net area of this length and this length. So net area of connecting length will be total 75 minus this area, this bolt area 20 minus 8 by 2. So this is our thickness 8 by 2. So net area will be at center of this. So that will be 408 mm. Same way if we calculate the area of our outstanding length, it will be 50 minus 8 by 2. Again take half to compensate the effect of doubling. It should not be double, so that's why we are dividing it by half, multiply by thickness. It will give us 368 mm square. Okay. Next thing is this outstanding width, leg width is 50 mm. W is equal to 50 mm. W1 is equal to 40 mm. 50 minus 10 of this thickness. And so the shear leg width BS will be W plus W1 minus T. You remember W plus W1 minus thickness. So same thing we are using here, 50 plus 40 minus 8. So after calculating this shear lag width, BS is given as is 82 mm. Then length of end connection LC, length of end connection LC will be given as 3 into 50 because 3 number of bolts we are using. So multiplied by 3 we are getting 150 mm. Then beta value will be the formula given as 1.4 minus 0.076 BS upon LC into W upon T into Fi upon Fu. So BS we have calculated as 82, LC calculated as 150, then W is given to us as 50 outstanding width. Then T thickness of our plate is 8 mm. And the next thing is Fi. For Fe 410 grade we are using Fi as 250 megapascal, so 250 divided by Fu, ultimate strength will be 410. Calculating all this value we are getting our beta as 1.25. So what is the check? That our beta value should always be greater than equal to 0.7, which is satisfying. Other thing is our beta value should be less than Fu and gamma m0 divided by Fi gamma m1. So applying that formula, it should be less than 1.44. So it is satisfying both the conditions. So we will take beta as 1.24. Okay. Okay, if this question is clear, then we will go to the next question. So next question is an ISA 90 into 60 into 12 mm is connected along the longer leg to a gusset plate by 3 bolts of 20 mm diameter and 4.6 grade in a line at a pitch of 55 mm and edge distance of 30 mm and gauge distance of 45 mm. So calculate the value of minimum gross and net area and shear along both lines parallel to the external force and in tension from the bolt wall to the toe of the angle perpendicular to the line of forces. So we have to calculate these 4 areas as we have seen before that AVG and AVN are in the direction of force, and ADG and ATN are in the perpendicular direction to the force. So we have to calculate all four areas. So what is given to us? Diameter of bolts 20 mm, then diameter of hole will be 22 mm. So area AVG, like cross area in the direction of loading, will be given as 12 into thickness into 2 into 55. So 2 into pitch distance plus 30 edge distance. So 2, 3, 4. So this is our pitch distance, 2 times into our pitch distance plus our edge distance. So this is our AVG. Okay. Second thing is AVN. So in case of AVN, we are neglecting the effect of our diameter. So effect of our bolts. That's why we are subtracting 2.5 into 22 from the complete area. So that will give us 1020 mm square. Next thing is in this direction, if we have to calculate ATG. So in this direction, what we are getting, we just have the gauge distance in this direction. So it will be thickness into gauge 540 mm. And then last is the ATN. Again, we will neglect the effect of our bolts. So in this case, we have only one bolt, so that's why we are multiplying by 0.5. So 45 minus 0.5 into 22. This will give us the area in tensile direction, ATG. So using this 4 area, we can say that correct answer is option C. Okay. This answer is clear to everyone. Okay, then we will go to the next question. An angle section of Fe410 grade steel and net area 976 mm square is connected to a gazette plate. 2 poles are provided along the length in the end connection. Calculate the approximate valve of the rupture strength of net section for Denhamberry sizing. So what is given to us for 2 bolts? Our alpha value will be 0.6. Second thing is for Denhamberry sizing, the rupture strength is given by alpha A and Fu upon gamma M. So for 2 bolts, alpha is 0.6. Then A in that area, AN is already given to us 976 mm square. For Fe410, ultimate strength will be 410. Gamma M1 is partial safety factor 1.25. Okay, using all this formula, we are getting TDN as 192 kilonewton. Okay. This is just to convert the units. Answer is A, 192 kilonewton. Fine. Okay, then we'll go to the next question. An ISA 80 into 50 into 8 angle of Fe410 grade steel is connected to a 14 mm thick gusset plate by weld as shown in figure below. Calculate the design tensile strength of the angle governed by rupture of net section if the gusset is connected to the shorter loop. Take gross area for ISA as 978 mm square and beta value as 0.82. So this is the angle section we are using, and they are telling our gusset plate is connected to the shorter length to the 50 mm length, and what else is given to us? The thickness of our gusset plate is 40 mm. Yeah. So how we will calculate this thing? First thing is we will calculate the net area of the connected leg. So net area of the connected leg will be 50 minus 8 by 2. Why we are doing 8 by 2? To neglect this double effect. So that will be multiplied by thickness of our angle section, 368 mm square. Second thing is the gross area of outstanding this length. Again we are doing same thing, 80 minus 8 by 2 into 8, 608 mm square. And then what we have to simply calculate, we have to calculate the design tensile strength of the angle section. So this is area we have calculated along this direction, along this direction. So net cross sectional area will be the summation of both the area, which is given as 976 mm square. So from the gross area, we can directly calculate the design tensile strength. It is given as 0.9 FUANC divided by gamma m1 plus beta FIAGO divided by gamma m0. So these formula we have already seen in our theory part, where we are telling if it is weld connection, what would be the design strength. So this was the formula we are using. So putting all the values, Fu will be given to us 410. A and C we have calculated, net area of connected line, gamma m1 1.25, then Fy will be 250, AGO we calculated as 600 A, and then gamma m0 will be 1.1. So this is coming as 223.2 kN. Then so the answer will be 220 to 225 kN. Okay. Okay, if that is fine, then we will go to the next question. Consider the statement in question 9, the question we have done previously. Now we have to calculate the design tensile strength of the angle governed by block shear failure if the gusset is connected to the shorter leg. So all conditions are same. What we are telling, we have to calculate design strength governed by block shear failure. So these are the, for block shear failure we need 4 area. Same way we are calculating these area, ABG, ABN, then ATG and ATN. Same thing as we have seen in previous question. It will be, first if we see this thing. So this is 65, the welded area. So 65 into gusset plate thickness 40 into this thickness, this length 50. Oh sorry, 50 will be the different one. 65 into 40. Our gusset plate is connected in this way. So in this direction it will be 65 into 40 into 2 times, because of 2 direction. We will sum them. Then same way AVN. Since there is no bolt connection, so our ABG and AVN will be same, and our ATG and ATN will be same. So ATG will be 50 into 40, ATN will be 50 into 40. Okay. So all 4 areas we have. Then again we will calculate the design strength due to block shear failure using the same formulas as we have used before. AVG into Fy divided by under root 3 gamma m naught plus 0.9 Fu ATN upon gamma m1. So putting all this value, we are getting our design tensile strength because of block shear failure as 445. So it will come in the range of D. Second thing is, we saw two formulas. In first case, AVG Fy upon under root 3 gamma m naught. In other case, these will be repeating. Like for AVG and ATN, one formula, and AVN and ATG, this formula. So using both formulas, we are calculating our design strength, and minimum of these two we will take as the design tensile strength of our system. Okay, so it will be 445. So answer will be D, 445 kilonewton. Okay, so that's all for today's session. In case you have any doubt, you can ask me now. We can close the class for today. Okay, if there are no doubts, then close the class for today. Thank you.